steel frame design on cold formed steel, and also known as light gauge steel, even though it's the same density. So we'll go through some examples of how we use cold formed steel. And again, we'll split it into two. Part A, we'll look at the analysis and design of frames. And then in part B, we'll look at the connections. And the connections are often quite critical in cold formed steel design. So here is a typical shed. One of the biggest users of cold formed steel are shed companies, and one of the advantages of sheds is they're an importance level 1 building, and so if it falls down on your tractor, nobody really cares. But they've extended the use of these sheds to houses and living accommodation. So we're now getting cold formed steel framed houses which started their life as sheds. That makes them importance level 2, which then gets them our interest, i.e. needs an engineer to sign them off. So there's kind of no giving away the fact that that started life as a shed, but now people are living in it. But you can get some quite good results. One of our biggest clients at Golden Homes, and they do cold formed steel framed houses. They're usually 1 or 2 stories, and they're made from a template. Now, unfortunately, you can't see the steel frame. Why would you? It's hidden behind all the cladding and all the linings. Another use for them is in warehouses, and this is for a company called Core Steel. And again, they use rather large cold formed steel sections to form workshops, warehouses, and so forth. So what you normally just see is the cladding itself. So in this case, the cladding is usually steel as well. The bracing is steel, usually quite light. And then the main frames and the purlins and the girts are nearly all steel as well. So this is what a Golden Homes house looks like without the cladding on. And it reveals its steel, cold formed steel sections hiding behind it. And there's no surprise. Basically, anything you do in timber frame, you can do in cold formed steel frame. That's the approach that we take. And that's the approach that the builders take as well. In this case, we can prefabricate large elements of it. And because they're relatively lightweight, 1 or 2 blokes can pick them up and move them around on site. You can basically transport the whole house, all the frames for a house, on the back of a trailer pulled by a ute. So you can have your prefabricated roof trusses in the same way that you've got prefabricated timber roof trusses. A quick shot at the ceiling framing. So we're going to be putting jib lining on the underneath of that. These whole wall frames can be prefabricated, brought as one piece, and then connected to the slabs below. You'll notice they've already got bracing in them, just as you would do in a timber framed house. For larger openings, we can have prefabricated lintels, long span lintels made up of the C-sections screwed together. And we need hold down bolts or screws to hold down the walls or the columns of that steel framing. A reminder, NASH is the National Association of Steel Framed Housing. This is the New Zealand branch of it, and they've produced a thing called the NASH standard. Part 1 is an alternative solution, and so what they're trying to do is turn NZS 3604, that standard for timber framed houses, into a national standard for steel framed houses, and it follows the same design approach. And the scope of the NASH standard part 1 is very similar to the scope of NZS 3604. Reason being, you're looking at two stories possibly, and it's a house, it's a residential structure, and it's nearly always lightweight. Part 2 gives you a lot more information about the design of the frames and the precast and the prefabricated sections. And the important part, of course, is the envelope. So as I reminded you, keep the water out So you need to put in flashings and gutters and so on. All of those can also be done with light gauge steel, as we call it. Just going through the Nash standard part 1, and they've got some nice pictures, diagrams to show you what each of the components is. So it's very similar in concept to a timber framed house. So you have load bearing walls as framed in light gauge steel. And obviously you need to have some bracing in there to take your lateral loads. And your floors can even be in light gauge steel joists, and even your bearers. You'll probably put it possibly on timber or steel subframes. Here is a typical floor in light gauge steel, and this explains the terminology that's used. So your floor bearers and your floor joists and how it goes together. Similarly, you've got components of a typical steel framed wall. Now the bracing can be built in the prefabrication yard. You can have your K bracing or cross bracing, or you can have additional strap bracing. These are very thin steel straps that connect things together. And once it's all up, you can connect the whole thing together. Similarly, in the roof, you've got your prefabricated sections of your roof trusses. Those can be braced together with these very thin steel straps. Yeah, if you want to calculate the loading on your ridge beam, it's simple as that. Take half the trib area on both sides, add it together. Similarly with an intermediate beam. Going down into more detail, what do we do with our bottom wall plates? How do we fix it to the base? And how do we accommodate that? Now, there are a number of ready-made lintels that are used as standard, and for the small, short openings, these can be relatively simple Pratt or Warren trusses with these channels screwed together. If you've got longer spans or heavier loads, you can add plates to them until you get the full depth plates, which ends up basically being a box beam, all nicely screwed together. So you can use the steel frames on a timber floor, timber subsystem, or even a concrete floor. It's much simpler if you just do it on, you've got a concrete raft, for example. Here's one I prepared earlier. So this is the one I'm working on right now. I didn't do the design. I'm doing the PS2 for this. So we mentioned Core Steel before. Their specialization is in large warehouses and workshops, usually for industrial clients. And so all the main members of that are done using light gauge steel, using rather large sections. So you've got portal frames. Surprise, surprise, they're built up. Now, some of them are 400 mil deep and some are over 600 mil deep in there. So that's quite big for cold form steel, but it shows how far you can push this basic technology. And the crucial thing is how they're joined together, because the connections in light gauge steel is usually the critical factor. This is from a previous job. This was somebody's house. And he likes a lot of open plan spaces, and he liked kind of workshop style areas for his house. So we get a 3D model like that. So the fabricator will put that together, ready for fabrication. We can import that using, in this case, it's a vertex viewer. So we can manipulate that in 3 dimensions. I won't show you that at the moment because you need a decent connection to view it. But basically, I'm sure you've seen 3D models. And you can maneuver around it and to get each of the components. This is our bit of it. Here are some of the typical trusses we use and how we put them into multi-frame frame analysis. So on the left, we have our analysis model showing the members and the nodes and elements of that analysis model. We've added the loads, dead load, live load, and we get our analysis results. And so we have our deviations or deflections of the frame under various load cases. Quick look on the plan, you've got lintels around, and you need to design those lintels because it's carrying the roof down to the flank walls over the windows. And as you've seen before, I've got ready-made lintels prefabricated lintels. Here's an example of another light steel frame house. This is kind of the artist's impression we got. I think it's come from Google SketchUp. The fabricator sends us this. That's like what they want to produce. And the architect has produced a section through it. So it's a 2-story steel framed house. Lower floor plan, upper floor plan. Here is our 3D analysis model from that. We've put this into multi-frame and we get our wind load model from that. Once we've analysed it, we can get the analysis results out. So we can see the bending moments on each of the frames. Then we need to design those. So multi-frame will design light gauge steel and it will produce a report, whether it's under or over. And again, you need to be careful of the deflections and you need to know where the restraints are. If you assume everything's fully restrained, you're probably wrong. So you will have restraints from your purlins and your girts, which minimizes your effective lengths of your members. There's also a thing we use called cold steel 4600, and I think that came out of the University of Sydney many years ago. And so if you just want to design a girt or a purlin or single element, then you have this piece of software. And so you select the section, in this case it's a lipped hat or a top hat style. It's 150 by 0.95, so it's less than a millimeter thick. And we're using grade 500 steel. We add our inputs in terms of the loads applied, the axial load moments and shears, tell it what the actual lengths and what the effective lengths in axial load and bending are. Let's have a look at the section itself and the section properties it's generated. And then we run it through a design check and it says happily that it is safe. We've got a safety factor there of 1.17. So quite efficiently designed, put it that way. Right, we've got time to go through this, which is what's going on behind the software. As I say, if you really want to understand software and how software works, if you really want to understand a code of practice or a standard, you pretty much need to go through it line by line, and reading the standard really isn't good enough. You need to use it. And one way of using it, well, the old-fashioned way was you wrote down it by pencil and paper. Well, the modern day pencil and paper I regard is MathCAD. This is a MathCAD file for this particular channel. And so I'm quite explicit in the design. And so this is basically what I call electronic ink. This is the sort of calculation I would have done by hand in the past. But now we've got MathCAD and other tools that we can use. So you put in the basic parameters, depth, width, and thickness, and so forth. And you can derive the section properties from the formula given in standard text. So dimensions to the neutral axis, second moment of area about major and minor axes, and the polar moment, inertia, and the torsional constant pop out. There's a number of properties that are defined in the code, AS/NZS 4600. And these are pulled out of there, which is all to do with buckling and warping. And from that, you can derive a warping constant and a polar radius of gyration. Put in our material properties and our applied loads. And first check is check it in axial tension. Now, light gauge steel is normally quite good in axial tension because you just basically take the gross area or net area, if you want to remove the fixing holes, and multiply it by either the yield or the ultimate tensile strength as given by equation 3.2.2. So your tensile capacity is 26. That's a decent capacity for a tiny bit of metal. What channels and light gauge steel are not so good at is bending. If you start bending it, it wants to, well, yield. Look at the yield capacity, and that's simply the section modulus multiplied by the yield strength, and you apply a strength reduction factor to that. And one of the things about light gauge steel is it's susceptible to buckling. And there are two approaches in the code 4600 give you. One is the effective area method, effective width method, and the other one is the direct strength method. So there's the two halves to the same approach. One is you reduce the amount of material that you can actually use at its full strength, or you reduce the stress that you can take. In old-fashioned terms, it's basically allowable stress design, as we used to call it. And so if you've got an outstand element like that, you've got an outstand of B and a thickness of T, your slenderness is quite high. So the end of your outstand is likely to start buckling before it starts yielding. And remember that structural engineering design is not just about yielding. Because the mechanical engineers, they think it's all about stress. And they think, well, with my von Mises stress is less than yield, so therefore we're good to go. And they completely forget about buckling. Members in steel design, whether it's hot rolled or cold formed, will usually buckle before they yield. So it's a geometric failure rather than a material failure. And for light gauge steel, that's doubly so. So in the world of hot rolled steel, most of our sections that we'll be using are usually compact, i.e. they're not usually subject to local buckling. Local buckling is not normally the governing factor. But light gauge steel, local buckling is quite often your factor. So we've got an outstand there of 29 millimeters, and we pull out a plate buckling coefficient to give us our elastic buckling stress, FCR. We work out what our slenderness ratio is. We then get a reduced effective width factor from which we can derive our effective width. So instead of being 26 millimeters wide, it's only 13 millimeters wide. It's halved because the rest of that outstand is useless in bending because you're trying to squash it. And before it squashes, it will buckle out of the way. So then you can derive a whole series of properties for your reduced section. Similar as we did before, an effective area, dimensions to the neutral axis, second moments of area, section modulus, and so on. And so you then have an effective section capacity. Now remember, you're just on the section capacity. You've looked at the yield, now you've looked at the local buckling. So far, you've not looked at the length of the member. So let's have a look at that. So we're saying our effective lengths are 2 meters at the major axis and 1 meter about the minor axis. So we've derived our section modulus from above, our yield moment. Then we need to consider the effective elastic flexural buckling stress, which is given from a whole series of complicated calculations given in the back of the code, Appendix D. And you go through those, and they are related to the slenderness of the element you're looking at. So that's where the effective lengths come in on the major and minor axes, which gives you your elastic buckling moment based on that, which is considerably smaller than the yield moment. Okay, so you can spit it out and you get design moment capacity. You've taken the smaller of it as 0.26. For completion, you need to look at shear. So when your computer is spitting out shear capacity, this is what it's doing. The first check is your standard shear capacity. It's the material that's failing in shear. So it's basically your effective shear area multiplied by your yield strength multiplied by fiddle factor, in this case 0.64. Okay. You can also look at the shear buckling. So again, buckling for slender webs can be an issue. In this case, it's not, because our shear buckling value is bigger than the shear capacity. And so you take the minimum of those. You need to check combined actions. So combined bending and shear in this case. If the combined squares of the utilization ratios are less than 1, you're good to go. Have a look at bearing, because these things are sitting on something, and you've quite a large bearing capacity there. Again, quick check on combining the bearing stress with your bending stress, and you find that's generally okay. This is a bit of a fiddle because we're applying our largest moment where the bearing is largest, so that's a little bit conservative. You then check members in axial compression. So It's unusual to go through all these things. You go through the ones which are most appropriate. Your software will spit out everything for every element, most of which is probably irrelevant. But for the sake of completion, I've done it in this MathCAD. So you take your full section capacity, as we've said, it's just the area by the yield strength. That's a nice high of 29 kilonewtons. It's quite a lot for a very thin bit of metal. But of course, it's going to buckle before it reaches that. So you need to derive what the elastic flexural buckling stress is. And this is a similar to what we've done for bending, except it's a different set of formula and a different set of parameters to get out a different set of stress. So 4600 works in stresses all the time. And it works out in basically your buckling stresses, and then you apply it to find your capacity based on the effective section modulus. So we work out what our buckling stress is and apply that. We have a maximum axial capacity of 6.9, so a lot less than the gross section capacity. You've got another check for axial capacity for local buckling. So we did local buckling for bending. You also need to do local buckling for axial capacity. Why, you say? Because the stress distribution is a bit different. So in axial compression, you're assuming you've got uniform stress applied, where in bending, you've got bending stress applied. So you've got going from compression to 10 at the top to compression in the bottom, if it's a beam, for example. So if you've got a wall element, and some of these elements are supporting vertical loads and horizontal loads and are acting as bracing, you'll have multiple load cases and multiple design action effects. One of them might be bending, the other one might be axial load. And you need to check the effective area that you can actually use for this. And again, we've got our outstanders 29.5, and running through the calculations, we get a design compression capacity of 4. Again, a lot lower than the actual gross section capacity. Check on combined compression and bending, because you can only use that material strength once. And so therefore you need to combine the applied stresses in such a way that gives you the maximum and make sure your applied total stress is less. Now, there are a number of combinations you can do. So you combine bending about the major axis, bending about the minor axis with axial compression, and that's what you need to check. If it's less than 1, and again, we're good to go. So there's an awful lot of checks to do. Final check in terms of combined tension and bending, not normally an issue, but just to check for the sake of completion, and you get the lot. And a design summary. So here's our axial capacity and compression, and our buckling capacity, our bending capacity, and our lateral torsional buckling and our local buckling capacities about the major axis and the minor axis. And finally, our shear capacity. If all those are less than the applied, then you're good to go. Right, we'll have a brief pause for questions.